Okay, so we can continue then. So these settings, yeah, we were thinking about these settings. So materials, we will just create material with constant permittivity. So geometrical objects. So in this model, it's shown that we have two parallelepipeds. Actually, we can just use one, because another one we can set by this background distance. Yeah, so we can create this brick, this lower brick, and then set background distance in plus z direction equal to the size of this upper brick. And that's it. We will have, like, essentially I'll have two bricks. So we will just use one brick. So the size of these bricks in transverse direction, in x and y directions. Remember, also in COMSOL, we've done this and discussed this, that you don't need very large size. Actually, the size in this direction is not important at all. So you can use arbitrary size. That means you should make it as small as you can. And the minimal characteristic size in your model is the size of the mesh cell. So you can estimate, the frequency, so you know the wavelengths, and you can estimate the size of the mesh cell. Yes, so you take this 1000 nanometers wavelengths, divide by refractive index, which is 2, so it's 500 nanometers, and then 500 nanometers you divide approximately by 5, and you get approximate size, minimal size of the mesh cell, so around 100 nanometers. So you can choose the size of this transverse dimensions of this brick around 100 nanometers or 50 nanometers, something like this. So these background properties, so we'll choose background distance in plus z direction equal to some parameter L background. Which again, also we've discussed this on COMSOL, that what kind of thickness we should choose in z direction. Yeah, something like lambda over 4 at least. For some problems, you need even maybe 1 or 2 wavelengths. But in these particular problems, actually just one mesh cell is enough. So why? Remember this. When we have chosen the size of this background around lambda over 4, lambda over 2, why we were doing this? Do you remember this? So we are doing this in waveguide problems a lot, also in some scattering problems. So when you have near fields, and you have near fields, and you put some, well, doesn't matter, port or PML boundary conditions, and you put it very close to the object, and there are near fields. So these near fields can get absorbed by the PML or scattering boundaries, whatever. And then you get like additional losses in your system, which shouldn't be there. So near fields, they are not they are not associated with losses in the system. So this is just the energy stored in the near fields near the structure. So in these problems, you need to put this boundary away from the objects to make sure that the near fields decay enough. In our problem, when we solve right now, we do not have near fields. We have only propagating plane wave, and this is far field. So we don't need to put this, to put these boundaries of the calculation domain far from the object. So we can do it just by one mesh cell, something like this. So all the sizes in all directions can be like of the order of one mesh cell, and this will be the minimal size of this. So let's set this in CST. So let's create materials. So on the left, there is a folder material. Well, there are two options pretty much always. So you can find these materials in the like in the modeling tab. Just look at the folder on the left. I think it's easier. Find this folder materials, right click, and then choose proper option like new material. Okay. Choose the name, like dielectric. Epsilon equal to 4. Remember that it's always best to use variables, not just numbers. So you can create a variable, something like eps dielectric. And once you click OK, so you haven't defined yet this eps dielectric parameter. So cst will suggest you to assign some number to this variable. And eps dielectric is equal to 4. So after that, click OK, and yeah, that's it. So now you have this new material. Also, at the bottom, you have parameter list. You can see that now we have created this variable eps dielectric. Okay. Actually, yeah, remember that when we have defined frequency range, we just put here 300, 301. Again, it's better. Right now, it's not important, but it's better to always use variables. Because then if you want to just change some parameters, you won't need to go to all of these settings and to check where you have used numbers and where you have used variables. Okay, let's go further. So yeah, in CST, you can see by default, you have vacuum and you have perfect electric conductor. So we don't need to create second material. We already have material vacuum with epsilon equal to 1. So we created materials. Now let's create this one brick, so geometrical object. So you can go to modeling tab and choose this first geometry object brick. So once you click on it, CST will like suggest you to draw this brick. But I think it's better if you just click escape, and then the dialog box will open where you can define the coordinates of this brick, the size and so on. Material. So this will be the electric layer, let's say. Again, we will use variables everywhere. So we will put for in x direction, it will be minus Lx over 2 to plus Lx over 2. In y direction, it will be from minus Ly over 2 to plus Ly over 2. And in z direction, so we will choose this interface coordinate z equal to 0. So this means that the electric will be from minus Lz, let's say, from minus Lz to 0. And then you need to choose material, this new material that you have created, the electric. And after you click OK, again, because we haven't defined Lx, Ly, and Lz, CST will suggest you to assign certain values to these parameters. So, yeah. that mean and that max are the coordinates. Yeah, so so you can create parameters, first create parameters, then use it. Or you can just put here something like Lx. So this parameter is not created yet. But after you click OK, the cst will ask you what is the value of this parameter. So if you just type here like, from minus Lx over 2 to plus Lx over 2 like this, and then click OK, the cst will ask you what is the value of these new parameters. So for that mean you need to type something from minus over to 0, to 0, and that's it. Click OK. So as we discussed, the size should be something around 100 nanometers or so. So we can choose for Lx, for Ly, and for Lz everywhere 100 nanometers. So then you should have this kind of brick. Okay. So we have this lower brick, and the upper half space we will create by using background distance. Tab, there is an option background. Yeah, actually, maybe let's first, so close this one. Let's first open boundaries. Let's set boundary conditions, and then we return to background. So there is boundaries. So boundary conditions. So by default, you have open add space. So open is essentially PML layers, and add space means that there is background distance, non-zero background distance between the object and the boundaries. So yeah, you can see that right now, the boundaries of calculation domain are far from the object. And we need them to be like in touch. So instead of open at space, if you just change it to open, you can see, this background distance disappears. So we're going to use, as we discussed, in transverse directions, we're going to use periodic boundary conditions. And in that direction, normal direction, we'll use open. So open, actually, it shouldn't matter because we will use ports for excitation and for collection, it doesn't matter. But in general, if you don't use ports, you can use open boundary conditions. So open in that direction. So in X and Y, there are two types of periodic boundary conditions here. So periodic, which is generally periodic, which you can use for different kind of problems. But there is also unit cell boundary condition. So we will use this one. So unit cell, it's specific boundary conditions, periodic boundary conditions. They are periodic in both X and Y directions. So you cannot choose unit cell in one direction. It should be always all four directions. And once you use unit cell boundary condition, CST will automatically create Floquet ports, which are very useful if you want to calculate some kind of diffraction problems. Let's see. This is essentially also we're solving diffraction problem, but we have only zeros diffraction order, or just reflection and transmission. Okay, so we use unit cell boundary conditions. Z-min is Z-max are open. Also, there is a tab scan angles where you can define the incidence angle for the plane wave. So since we're going to use normally incident wave, we just leave it as 0 and 0. So for now, it's fine. So you only need to choose unit cell and open. Okay, after that, you can click OK. Now you can see maybe, or maybe not very clearly, that the boundaries of calculation domain coincide with the boundary of this object. It's hard to see because they are right on, like they are the same. So let's now go to background distance, to background option and change background distance. So by default, the material of the background. So once again, so all this space between this inner rectangular parallelepiped and the boundaries of calculation domain are filled with certain material. So you can change the type of material here. By default, it's normal, and it means it's vacuum. Sorry?
What does it mean that it's normal?
Normal here means it's vacuum. So you can check properties here, click properties and see that this is a material with epsilon and mu equal to 1. So this is vacuum. But you can change it to other material if you need it. For now, this is exactly what we need. We need to fill the upper half space with vacuum. So it's, by default, it's vacuum, so it's fine. So here it's 0, 0, 0, 0, and in upper Z distance, we put also LZ. So put LZ, click OK, and that's it. So we've set the background distance. If you do not have this boundary of calculation domain, you can right click on the screen and click bounding box. And then CST will show you the boundaries of the calculation domain. So, okay, now the geometry is what we need. So 2 layers, upper half is vacuum, lower half is dielectric. Boundary conditions are set. So, yeah, we're almost there. So the last settings. So first two are source of radiation and results. So we need to understand what we're going to use as a source and what kind of results we would like to obtain. So since we're using unit cell boundary conditions, we'll have Floquet ports. Floquet ports means that you take a arbitrary field distribution in 2 dimensions and decompose it into Fourier series. And then you have different Fourier harmonics. You can always do this because you consider periodic system in XY direction. So the zeroth Fourier harmonic corresponds to the homogeneous distribution of the field. And that means it's exactly plane wave. So we will use the zeroth harmonic of the Floquet port as the source and also as the port that will absorb the radiation at the lower boundary. So we don't need to create this, it's created by default. We only need to check that we have these first modes available there. What we want to obtain as the result. So as soon as you have ports in your system, cst will automatically calculate you as parameters, scattering parameters, which relate amplitudes of different modes and different ports. So here we're going to have just 2 ports, and each port will support 1 mode. That means that we will have just scattering matrix 2 by 2. So we will have S11 will be reflection coefficient, S12 will be transmission coefficient. Actually, we will have only 2 of these 4 4 scattering parameters, because we will use only 1 port as the excitation port, similar to COMSOL. Also, if we want fields, maybe we will have time for this. So we can create a field monitor, and then so the CST will then calculate you the field distribution at this frequency. So for now, let's just calculate scattering parameters. So let's check. So Floquet ports are in the folder ports. So once we defined unit cell, we have this Zmax and Zmax and Zmin Floquet ports. So if you click on, let's say, Zmax, you can see that by default you have 18 Floquet modes. So you know that in this problem you don't have any diffraction, just you have zeros diffraction order. So this means you don't need all these Floquet modes. You need only first 2. Actually, well, any one of the first 2, because first 2 modes are plane waves which differ only by polarization. Yeah.
We have different settings.
Okay, we'll check this. So right now you need to change number of Floquet modes to 1 in Zmax and also in Z. Yeah. You don't even care. Yeah, you haven't set the frequency range, so you need to actually yeah, just 1, because first 2 Floquet modes, these are plane waves with 2 orthogonal polarizations. So we don't care which one. So because we consider isotropic system, so in XY direction it's isotropic, so we can choose either of them. So just 1 is enough. But you need to change it for both Zmax and Zmin ports.
Shouldn't we set the polarization?
So, well, we do not care for this particular problem. We don't care whether it's polarized along X or Y. So we can choose either of them. You can check if you click details, you can see that, yeah, you have these first modes there, TE, TM. So, but then anyway, you need to understand what is called TE, TM in this particular case. So it doesn't matter right now. Yeah, both of them will give us the same result for scattering parameters. So once we define these 2 modes, Okay, yeah. So then I think we need to check what mesh we have. So CST builds this mesh by default using approximately 4 cells per wavelength. So if you go to Home tab or Simulation tab, there is a mesh view. So once you click it, you need to click Update, and then CST will build the mesh. Yeah, no. So you need to. So if it doesn't show you the mesh, you need to choose components. You need to choose which components. Okay. Okay. Zero. Okay, you can see that it's not what we expected. So we wanted to have something like one mesh cell for the size of this brick, but we have more like 10. So this is because you see there are two lines in this mesh. First you can open global properties in the mesh view, and there are two lines. So first says how many cells per wavelength. So you can choose cell per wavelength and just put certain number there. By default, you see it's 4. So if you choose automatic, it means that CST chooses something like 4 cells per wavelength here. That's what we were aimed at. But there is also the second line, which says cells per max model box edge. And in our case, we have this dielectric layer, which is, that's the only object we have. So the max model box edge, it's this 100 nanometers. So it's just the size of this rectangle, maximal edge of this rectangle, rectangular parallelepiped. So, and here it says 10 cells per this 100 nanometers. And because of this, we have 10 mesh cells in like this brick is divided into 10 mesh cells. So that's not what we need, yeah. So typically we can just set it to 1. So if we set it to 1, that means basically that this property is not important. It doesn't matter. So everything is based on the first line. And first line just says, just like build mesh somehow. You can use specific number of cells per wavelength. It's not really important. So after you've changed it, you can check what is the number of tetrahedrons in the right bottom corner. So in my case, I have 24 tetrahedrons. If you have something like this, then yeah, that's it. That's what we need.
Open the mesh.
Okay, so we I think ready to launch the model. Let's see. Yeah, also important parameters. Solver settings. This is the last parameter that we need to change. So we go to Home tab. So click not on this arrow, but just on the button, on the green button, and you will open solver settings. So right now, yeah, we're not going to discuss all of this. Let's just change some of these parameters. So first in the method. So since we only want to calculate this problem at one particular frequencies, we change it to discrete samples only. So that means that we're not going to use any kind of broadband calculation. We just calculate at specific frequencies. Second, so mesh type, we will use tetrahedral. It's typically better. Now, source type. So we will use Z-max port. Yeah, so the plane wave propagates from vacuum. So we use Z-max. So since we set only these Floquet ports to have one mode, we have only one mode. So it doesn't matter whether it's all or TE. And also, so by default, CST will use adaptive tetrahedral mesh refinement, which means that you solve the problem, then CST somehow adjusts the mesh, makes it more accurate, solve it once more, then once more, and try to compare the results, whether the accuracy is increased. So sometimes it works, but in this case, well, we don't need it. We'll maybe discuss it later. The last thing in this list of frequency samples, you need to change. So to choose one active line. Yeah, so one active line and choose single frequency. So it should look like this. So that means that the program will make simulation at one particular frequency, at the exact frequency, which you set here, 300 terahertz. So you can click apply just to save these settings. But if you done everything correctly, then you can just click start. So the CST will ask you whether you want to enable adaptive mesh refinement. You don't want it. So click no, and that's it.
Oh, it's to change it, and we have, yeah, that's okay. There's something on the
Okay, once the simulation is finished, you have results also on the left in this folder. So we are interested in 1D results as parameters. So we have these two as parameters, S11, S z max 1, z max 1, S z min 1, z max 1. So this 1 in the brackets is the number of the mode. And z max and z min are the name of the ports. So the first one means that this S parameter relates amplitude of the first mode at z max port to the first mode of the z max port. So it's reflection coefficient. And the second parameter relates first mode of the z max port to the first mode of the z min port, which is transmission coefficient. So by default, they are plotted in decibels. So you can change it in this 1D plot. Instead of decibels, choose linear. I think linear, it's more convenient in optics. So what kind of results we should have obtained? So what is reflection coefficient for the interface between vacuum and dielectric with refractive index 2? Do you maybe remember this? There's a simple formula.
What's the reflection coefficient?
Yeah.
N1 minus N2 divided by N1 plus N2.
Yes.
Square.
Yes. So square, well, the square is, well, okay. So first, yeah, if you're looking at there are amplitude reflection coefficient, which is generally a complex one. So it relates complex amplitudes. And there is energy reflection coefficient, which relates the intensities. So if you want amplitude complex reflection coefficient, it's simply N1 minus N2 divided by N1 plus N2. If you want energy, then you need to take square modulus of this. So in our case, so we have minus 1 divided by 3. So this should be the reflection coefficient. Well, you can see that, yeah, it's pretty much it. So just maybe 1% error or something like this. This is, so here we have plus because we plot linear. So it's modulus of this. If we plot real, okay, well, yeah, we actually, so how to say this? So it's, so this amplitude reflection coefficient, it relates amplitudes. So it depends on the phase, and phase depends on the distance that we chose. Yeah. So if we chose the boundary slightly far from the interface, then the wave would propagate more distance, its phase would change, and the phase of the reflection coefficient would also change. So actually this phase, well, it's not important here. So we can look at just at linear reflection coefficient.